Salut tout le monde. Welcome back to another differential geometry stream. I'm Anthony, and today, of course, we are going to be continuing to read from Differential Geometry by Erwin Kreyszig. We are in chapter 4, which has been on the second fundamental form, Gaussian and Mean Curvature, and we're actually going to finish that chapter today. Keep it kind of nice and short with just 2 sections. I know I really like the longer, 3, 4, maybe even 5 sections or more long videos, but being that we're at the end of this chapter, I figured it's better to just finish this chapter and then start the next chapter, which is on geodesics, in a completely new video. But yeah, in today's video, we're going to be reading from section 47, which is on properties of Christoffel symbols, which were introduced 2 sections ago. So in the previous video, which was in section 45 for the formulae of Weingarten and Gauss. And specifically, we're looking at a surface in 3-dimensional real space, and you have this surface where you have these coordinate dimensions defined on the surface, and with respect to tangent vectors in those coordinate dimensions, you can thereby define a normal vector. And before we did all this stuff with Christoffel symbols, we also had tensors, which heavily used with contravariant and covariant indices, heavily used subscripts and superscripts, and then it made things even more confusing when we introduced the summation convention, which is basically just dropping the capital sigma with the summation index and the bound of the summation, just getting rid of that. So, but then we have these Christoffel symbols now, which again are using the subscripts and superscripts a lot. And so I could definitely see where it could get a little bit confusing with all of that at this point. So I guess as a recap, we have here at the bottom of page 140, we have capital gamma, which is a Christoffel symbol, and I refer to that just simply as Christoffel. So we have Christoffel sub alpha beta lambda equals the scalar product of x sub alpha beta and x sub lambda. So x sub alpha beta in this case is partial squared x, partial u alpha, partial u beta. So it's a second order partial derivative with respect to u alpha and then u beta, where those are the coordinate dimensions that are defined upon the surface in 3-dimensional real space. And then this x lambda is either, you could say, x1 or x2, being like a tangent vector in the, let's say, u alpha, and then the u beta coordinate dimension for either x1 or x2, let's just say. That, I'm pretty sure, is what these Christoffel symbols mean, and that's just the Christoffel symbol of the first kind. But it also continues to go on here on page 141, and I read this in the last video. This is just a recap, but it says, we mentioned that the Christoffel symbols do not form a tensor. Their transformation behavior and further properties will be considered in section 47. And with that, that is where I'm going to start reading section 47 from. So on properties of the Christoffel symbols. The Christoffel symbols were introduced in section 45 in connection with the formulae of Gauss. Since these symbols will be frequently used, we present a short collection of their most important properties. The Christoffel symbols of the first kind are given by the expressions Christoffel sub alpha beta lowercase gamma equals vector x sub alpha beta scalar product with x sub lowercase gamma equals 1/2 times the quantity partial g sub beta gamma partial u alpha plus partial g sub gamma alpha partial u beta minus partial g sub alpha beta partial u gamma, for which refer to the notation previously stated for a Christoffel symbol of the first order. Christoffel sub alpha beta gamma equals the scalar product of x sub alpha beta with x sub lambda with x sub gamma, and the previously given representation of the Christoffel symbols of the first kind in terms of the first partial derivatives of the components of the metric tensor. From this relation, we obtain the Christoffel symbols of the second kind. Christoffel sub alpha beta superscript sigma equals g superscript sigma gamma times Christoffel sub alpha beta gamma, for which referred to the symmetry properties of the covariant curvature tensor in general and properties in the case of surfaces in 2-dimensional Riemannian space. Using the previous relation for the Christoffel symbols of the first kind given in terms of partial derivatives, in terms of the first fundamental form, and x superscript sigma equals g superscript sigma gamma times x sub gamma, for which referred to section 32, we have that Christoffel sub alpha beta superscript sigma equals equals the scalar product of x sub alpha beta with x superscript sigma. From the previous relation for the Christoffel symbols of the second kind, it follows that g sub gamma sigma times Christoffel sub alpha beta superscript sigma equals g sub gamma sigma times g superscript sigma lambda times Christoffel sub alpha beta lambda, which equals Kronecker delta sub gamma superscript lambda times Christoffel sub alpha beta lambda, which equals Christoffel sub alpha beta lowercase gamma. That is, Christoffel sub alpha beta lowercase gamma equals g sub lowercase gamma sigma times Christoffel sub alpha beta superscript sigma. And for this, refer back to the relation Christoffel sub alpha beta lambda equals g sub lowercase gamma lambda times Christoffel sub alpha beta superscript lowercase gamma. Since x sub alpha beta equals x sub beta alpha, the Christoffel symbols are symmetric with respect to the first two indices. Namely, Christoffel sub alpha beta gamma equals Christoffel sub beta alpha gamma, as well as Christoffel sub alpha beta superscript gamma equals Christoffel sub beta alpha superscript gamma. See again the symmetry of Christoffel symbols with respect to their first two indices stated 2 sections earlier. Consequently, in the case of two-dimensional Riemannian spaces, that is, in the case of surfaces, there are 6 symbols of the first kind which are different from each other, namely Christoffel sub 111, Christoffel sub 112, Christoffel sub 121, Christoffel sub 122, Christoffel sub 221, and Christoffel sub 222. And the same holds with respect to the symbols of the second kind. The first partial derivatives of the coefficients g sub alpha beta of the first fundamental form can be represented as a sum of 2 Christoffel symbols of the first kind. That is, partial g sub alpha beta partial u kappa equals Christoffel sub alpha kappa beta plus Christoffel sub beta kappa alpha, which equals g sub lambda beta times Christoffel sub alpha kappa superscript lambda plus g sub lambda alpha plus Christoffel sub beta kappa superscript lambda. And for this, recall the relation partial g sub alpha lambda partial u beta equals Christoffel sub alpha beta lambda plus Christoffel sub lambda beta alpha. We will now obtain similar formulae for the components g superscript alpha beta of the contravariant metric tensor. If we differentiate the relation g sub alpha rho times g superscript alpha sigma, which equals delta sub rho superscript sigma, with respect to u kappa, we have partial g sub alpha rho partial u kappa times g superscript alpha sigma plus g sub alpha rho times partial g superscript alpha sigma partial u kappa equals 0. Taking the inner product of this expression and g superscript lambda rho, we obtain partial g sub alpha rho partial u kappa times g superscript alpha sigma times g superscript lambda rho plus partial g superscript lambda sigma partial u kappa equals 0. Hence, by means of the relations for partial derivatives of the coefficients of the first fundamental form given in terms of Christoffel symbols of the first kind, we have that partial g superscript lambda sigma partial u kappa equals negative partial g sub alpha rho partial u kappa times g superscript alpha sigma times g superscript lambda rho equals negative quantity Christoffel sub alpha kappa rho plus Christoffel sub rho kappa alpha closed quantity times g superscript alpha sigma times g superscript lambda rho, and therefore, in consequence of the relation for Christoffel symbols of the second kind, we have that partial g superscript lambda sigma partial u kappa equals negative g superscript alpha sigma times Christoffel sub alpha kappa superscript lambda minus g superscript lambda rho times Christoffel sub rho kappa superscript sigma. For the derivatives of the discriminant g of the first fundamental form, similar relations can be obtained. We have partial g partial u gamma equals partial with respect to u gamma of the quantity g sub 11 times g sub 22 minus the square of g sub 12 closed quantity, which equals partial g sub 11 partial u gamma times g sub 22 plus g sub 11 times partial g sub 22 partial u gamma minus 2 times g sub 12 times partial g sub 12 partial u gamma. Using the contravariant metric tensor, we obtain from this partial g partial u gamma equals g times the quantity g superscript 11 partial g sub 11 partial u gamma plus g superscript 22 times partial g sub 22 partial u gamma plus 2 times g superscript 12 times partial g sub 12 partial u gamma closed quantity, which equals g times g g superscript alpha beta times partial g sub alpha beta partial u gamma. Or in consequence of what was previously derived for Christoffel symbols and coefficients of the first fundamental form in this section, partial u gamma equals g times g superscript alpha beta times the quantity Christoffel sub alpha gamma beta plus Christoffel sub beta gamma alpha closed quantity, which equals g times the quantity Christoffel sub alpha gamma superscript alpha plus Christoffel sub beta gamma superscript beta closed quantity. Replacing the summation index beta by alpha, we find partial u gamma equals 2 times g times Christoffel sub alpha gamma superscript alpha, or Christoffel sub alpha gamma superscript alpha equals 1 over 2g then times partial u gamma, which equals partial with respect to u gamma of log of square root of g. We will now give explicit formulae for the Christoffel symbols in the case of surfaces. From the relation in the beginning of the section, we obtain Christoffel sub alpha 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 equals 1/2 partial g sub alpha alpha partial u alpha. Then Christoffel sub alpha alpha beta equals partial g sub 1 2 partial u alpha minus 1/2 times partial g sub alpha alpha partial u beta. Then Christoffel sub alpha beta alpha equals Christoffel sub beta alpha alpha, which then equals 1/2 times partial g sub alpha alpha partial u beta, where in all of these alpha does not equal beta. From the previous relations, we obtained that Christoffel sub alpha alpha superscript alpha equals 1 over 2 times g then times the quantity g sub beta beta times partial g sub alpha alpha partial u alpha plus g sub 1 2 times quantity partial g sub alpha alpha partial u beta minus 2 times partial g sub 1 2 partial u alpha, close both quantities. Then we have Christoffel sub alpha alpha superscript beta equals 1 over 2 times g then times the quantity g sub alpha alpha times the quantity 2 times partial g sub 1 2 partial u alpha minus partial g sub alpha alpha partial u beta, closed quantity minus g sub 1 2 then times partial g sub alpha alpha partial u alpha, closed quantity. And finally we have Christoffel sub alpha beta superscript beta equals, or rather is the same as Christoffel sub beta alpha superscript beta, which then equals 1 over 2g times the quantity g sub alpha alpha times partial g sub beta beta partial u alpha minus g sub 1 2 times partial g sub alpha alpha partial u beta, closed quantity. And in all three of these cases, alpha does not equal beta and do not sum. So these are not using the implicit hiding the summation convention, which was introduced in, I believe, section 27. Since in the case of surfaces any index can only take the value 1 or 2, it is clear what is meant by alpha does not equal beta in the first line of the relation for these Christoffel symbols. In the particular case of orthogonal coordinates, we have g sub 1 2 equals 0 and g equals g sub 1 1 times g sub 2 2. Consequently, in this case, Christoffel sub alpha 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 equals 1/2 times partial g sub alpha alpha partial u alpha, and Christoffel sub alpha alpha beta equals negative 1/2 times partial g sub alpha alpha partial u beta, and Christoffel sub alpha beta alpha, which is the same as or equal to Christoffel sub beta alpha alpha, which then equals 1/2 times partial g sub alpha alpha partial u beta. And of course, alpha does not equal beta, and Christoffel sub alpha alpha superscript alpha equals 1 over the quantity 2 times g sub alpha alpha closed quantity then times partial g sub alpha alpha partial u alpha, which equals partial with respect to u alpha of the logarithm of the square root of g sub alpha alpha. We also have Christoffel sub alpha alpha superscript beta equals negative 1 over the quantity 2 times g sub beta beta closed quantity times partial g sub alpha alpha partial u beta. And finally we have Christoffel sub alpha beta superscript beta, which is the same as or equal to Christoffel sub beta alpha superscript beta, which is then equal to 1 over 2 times g sub beta beta then times partial g sub beta beta partial u alpha, which is equal to partial with respect to u alpha of the logarithm of the square root of g sub beta beta. And in all three of these cases, alpha does not equal beta and do not sum. We have already stressed that the Christoffel symbols are not components of a tensor. We may obtain the transformation law of these symbols by means of the formulae of Gauss. Namely, x sub alpha beta is equivalent to partial squared x partial u alpha partial u beta, which is equivalent to Christoffel sub alpha beta superscript gamma times x sub gamma plus b sub alpha beta times n, where alpha can be 1 or 2 and beta can be 1 or 2. We have then that x sub alpha beta is equivalent to partial squared x partial u alpha partial u beta, which is equal to Christoffel sub alpha beta superscript gamma times x sub gamma plus b sub alpha beta times n, and x sub lambda over bar epsilon over bar is equivalent to partial squared x partial u over bar lambda partial u over bar epsilon, which is equal to Christoffel over bar sub lambda epsilon superscript sigma times x sub sigma over bar plus b over bar sub lambda epsilon times n over bar, where Christoffel over bar sub lambda epsilon superscript sigma are the Christoffel symbols of the second kind with respect to the coordinates u over bar 1 and u over bar 2. Since, on the other hand, x sub alpha is equal to x sub lambda over bar times partial u over bar lambda partial u alpha, and by differentiation with respect to u beta, x sub alpha beta equals x sub lambda over bar epsilon over bar times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus x sub sigma over bar times partial squared u over bar sigma partial u alpha partial u beta. We obtained from the previous relation that x sub alpha beta is equal to the quantity Christoffel over bar sub lambda epsilon superscript sigma times x sub sigma over bar plus b over bar sub lambda epsilon times n over bar closed quantity times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus x sub sigma over bar times partial squared u over bar sigma partial u alpha partial u beta. Since x1, x2, and n are linearly independent vectors for each of them, the coefficient on the right-hand sides of these two relations for x sub alpha beta must be the same. We thus find that Christoffel sub alpha beta superscript gamma times x sub gamma equals Christoffel over bar sub lambda epsilon superscript sigma times x sub sigma over bar times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus x sub sigma over bar times partial squared u over bar sigma partial u alpha partial u beta. Since x sub gamma equals x sub sigma over bar times partial u over bar sigma partial u gamma, we finally obtain the transformation law of the Christoffel symbols of the second kind. Christoffel sub alpha beta superscript gamma times partial u over bar sigma partial u gamma equals Christoffel over bar sub lambda epsilon superscript sigma times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus partial squared u over bar sigma partial u alpha partial u beta. In consequence of the Kronecker delta notation for doing changes of variables by multiplying different partial derivatives with each other, these formulae are equivalent to Christoffel sub alpha beta superscript gamma equals quantity Christoffel over bar sub lambda epsilon superscript sigma times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus partial square u over bar sigma partial u alpha partial u beta closed quantity times partial u gamma partial u over bar sigma. These two previous relations are sometimes called the formulae of Christoffel. By taking the inner product of both sides of the formulae of Christoffel and g sub gamma rho equals g over bar sub nu tau times partial u over bar nu partial u gamma times partial u over bar tau partial u rho, we obtain Christoffel sub alpha beta rho equals g sub gamma rho times Christoffel sub alpha beta superscript gamma, which equals g over bar sub nu tau times the quantity Christoffel over bar sub lambda epsilon superscript sigma times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus partial square u over bar sigma partial u alpha partial u beta closed quantity times partial u gamma partial u over bar sigma times partial u over bar nu partial u gamma times partial u over bar tau partial u rho. That is, the transformation law of the Christoffel symbols of the first kind is of the form Christoffel sub alpha beta rho equals the quantity Christoffel over bar sub lambda epsilon tau times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus g over bar sub sigma tau times partial square u over bar sigma partial u alpha partial u beta closed quantity times partial u over bar tau partial u rho. In the plane, there exist coordinate systems with respect to which the Christoffel symbols vanish everywhere. On an arbitrary surface, we may introduce coordinate systems with respect to which, at an arbitrary fixed point, capital P naught, the Christoffel symbols vanish. Indeed, if lowercase u subscript 0 superscript alpha, where alpha alpha can be 1 or 2, are the coordinates of capital P naught with respect to an arbitrary allowable coordinate system, and if the quantity Christoffel sub beta gamma superscript alpha closed quantity subscript 0 are the values of the Christoffel symbols at capital P naught, then the coordinates u star 1 and u star 2 defined by u alpha equals u star alpha plus u alpha sub 0 minus 1/2 times the quantity Christoffel sub beta gamma superscript alpha closed quantity subscript 0 times u star beta u star gamma, where alpha can be 1 or 2, have the desired property. That is, capital P naught is the origin of the u star sigma coordinate system. And by differentiation, we see that at capital P naught, A, partial u alpha, partial u star sigma equals Kronecker delta sub sigma superscript alpha, and B, partial squared u alpha, partial u star sigma, partial u star tau is equal to the negative quantity Christoffel sub sigma tau superscript alpha closed quantity sub 0, where u star 1 equals u star 2, which equals 0. As follows from the previous statement A, the coordinate transformation previously given is allowable in a neighborhood of capital P naught. By means of statement B previously read and the formulae of Christoffel, we find that at capital P naught, Christoffel star sub sigma tau superscript rho times partial u alpha partial u star rho equals Christoffel sub kappa lambda superscript alpha times partial u kappa partial u star sigma times partial u lambda partial u star tau minus the quantity Christoffel sub sigma tau superscript alpha closed quantity subscript 0, where u star 1 equals u star 2, which equals 0. Hence, by statement A previously read, Christoffel star sub sigma tau superscript alpha equals the quantity Christoffel sub sigma tau superscript alpha closed quantity subscript 0 minus quantity Christoffel sub sigma tau superscript alpha closed quantity sub 0 equals 0. And now, problem 47.1. Determine the Christoffel symbols corresponding to polar coordinates in a plane. Let x1, x2, and x3 be Cartesian coordinates in space. Then u1, u2, defined by x1 equals u1 cosine u2 and x2 by u1 sine u2, are polar coordinates in the plane x3 equals 0. We have g sub 11 equals 1, g sub 12 equals 0, g sub 22 equals the square of u1, and then we have Christoffel sub 122, which is the same as Christoffel sub 212 equals u1. We have Christoffel sub 221 equals negative u1, and we have that Christoffel sub 12 superscript 2, which is the same as Christoffel sub 21 superscript 2, equals 1 over u1, and Christoffel sub 22 superscript 1 equals negative u1, and all other Christoffel symbols vanish. Problem 47.2. Determine the Christoffel symbols of a surface of revolution represented in the form x of u1 and u2, which is equal to, entry-wise, u2 times cosine u1, then u2 times sine u1, then a function h in terms of u2. I had previously read that incorrectly in previous episodes where I would say that that's h times u2. It's not the case. The solution, we have g sub 11 equals u2 squared, g sub 12 equals 0, g sub 22 equals 1 plus h prime squared, Christoffel sub 112 equals negative u2, Christoffel sub 121, which is the same as Christoffel sub 211, equals u2, Christoffel sub 222 equals h prime times h double prime, Christoffel sub 11 with the superscript 2, then equals negative u2 over the quantity 1 plus h prime squared, and Christoffel sub 12 superscript 1, which is the same as Christoffel sub 21 superscript 1, equals 1 over u2, and Christoffel sub 22 superscript 2 equals h prime times h double prime over the quantity 1 plus h prime squared. All other Christoffel symbols vanish. Problem 47.3. Determine the Christoffel symbols of a surface represented in the implicit form x3 equals capital F of x1 and x2. We use the notations capital F sub alpha denotes partial capital F partial u alpha, and capital F sub alpha beta equals partial squared capital F partial u alpha partial u beta. And write the given representation in the parametric vector form x in terms of u1 and u2, which is given entry-wise by u1, then u2, then capital F of u1 and u2. Then x1 equals entry-wise 1, then 0, then capital F sub 1. x2 equals 0, then 1, then capital F sub 2, and x sub alpha beta equals 0, then capital F sub alpha beta. G sub 1, 1 equals 1 plus capital F sub 1 squared. G sub 1, 2 equals capital F sub 1 times capital F sub 2, and G sub 2, 2 equals 1 plus capital F sub 2 squared. Therefore, Christoffel sub alpha beta gamma equals the scalar product of x sub alpha beta with x sub gamma, which then equals capital F sub alpha beta times capital F sub gamma, which is equivalent to partial squared capital F partial x sub alpha partial x sub beta times partial capital F partial x gamma. From this, and a few other things that we're supposed to remember from previous sections, we obtain that Christoffel sub alpha beta superscript 1 equals G superscript 1, 1 times Christoffel sub alpha beta 1 plus G superscript 1, 2 times Christoffel sub alpha beta 2, which equals then 1 over G times the quantity sub quantity 1 plus capital F sub 2 squared closed sub quantity times capital F sub alpha beta times capital F sub 1 minus capital F sub 1 times capital F sub 2 times capital F sub alpha beta times capital F sub 2 closed quantity, which equals 1 over G times capital F sub alpha beta times capital F sub 1, which is equivalent to 1 over G times partial squared capital F partial x sub alpha partial x sub beta times partial capital F partial x1. And similarly, Christoffel sub alpha beta superscript 2 equals 1 over G times partial squared capital F partial x sub alpha partial x sub beta times partial capital F partial x2. We are now in the final section for chapter 4, section 48, umbilics. At point capital P of the surface capital S is called a navel point, or umbilic, if all normal sections of capital S at capital P have the same curvature at capital P. The point capital P is an umbilic if and only if, at this point, B sub alpha beta equals lambda of U1 and U2, then times G sub alpha beta, where alpha can be 1 or 2 and beta can be 1 or 2, where this factor lambda is independent of the direction of the normal section, for which refer back to section 41. For example, if we rotate the curve x3, which is equal to x1 squared, and x2 equals 0 about the x3 axis, we obtain a paraboloid of revolution which has an umbilic at the vector x equal to 0, 0, 0. In the case of an ellipsoid of revolution, the points of intersection of this surface and the axis of revolution are umbilics. We will now consider surfaces whose points are all umbilics. Theorem 48.1. If every point of a surface capital S which has a representation of class r greater than or equal to 3 is an umbilic, capital S is a plane or a sphere. The proof is as follows. In order that every point of capital S be an umbilic, the relation for B sub alpha beta equals lambda times G sub alpha beta previously given must hold at every point of capital S. First, consider case A, if you will, where if lambda equals 0, the coefficients of the second fundamental form vanish identically. That is, capital S is a plane, for which refer back to the previous problem 45.1. Consider conversely the case B, if you will. Suppose now that lambda does not equal 0. Since any point of capital S is assumed to be an umbilic, any curve on capital S is a line of curvature. Hence, from the formulae of Weingarten, as well as the previous relation for B sub alpha beta equals lambda times G sub alpha beta, we obtain that the vector n sub alpha equals negative B sub alpha alpha over G sub alpha alpha, then times vector x sub alpha, which is equal to negative lambda times the vector x sub alpha, where alpha equals either 1 or 2 and do not sum. It then follows from this relation that n sub alpha beta equals negative lambda sub beta times x sub alpha minus lambda times x sub alpha beta, and additionally lambda sub beta is equivalent to partial lambda partial u beta. Analogously, vector n sub beta alpha is equal to negative lambda sub alpha times x sub beta minus lambda times x sub beta alpha. By subtraction, we find lambda sub 1 times x sub 2 minus lambda sub 2 times x sub 1 equals 0. Since at regular points of a surface, x1 and x2 are linearly independent vectors, lambda sub 1 equal to lambda sub 2 equals 0 must hold. That is, lambda is a constant. Hence, by integrating the previous relation for n sub alpha, we obtain that n equals negative lambda times x plus c, where c is a constant vector. Scalar multiplication yields that the scalar product of n with n is equal to the scalar product of the quantity negative lambda times x plus c with itself. If we set lambda equal to negative 1 over r and c equal to negative x naught over r, then since the scalar product of n with itself is equal to 1, then the scalar product of the quantity x minus x naught with itself is equal to r squared. This is a representation of a sphere of radius r with center at x naught. And with that, we finish chapter 4 and we finish this video. I will see you guys in the next one next week.